This is joint work with my co-authors, Tom Bodanovic, Chinmay Nurki, and Henry Ewan, all of whom are here at the conference, and we'd all be happy to talk to you about this work. So what I'm going to tell you about is a new framework that turns any quantum error-correcting code with an efficient encoding circuit into an approximate quantum error-correcting code that is the ground space of a non-commuting k-local code Hamiltonian. I'm also going to tell you about a new depth-efficient analysis of something called the SpaceTime Circuit to Hamiltonian construction, which is used to embed parallel quantum circuits in the ground state of a local Hamiltonian. And that's actually the main technical contribution of our work. So, you come for the codes and you stay for the space-time Hamiltonians. Now, by applying this framework to good quantum codes with polylogarithmic depth encoding circuits, we're going to obtain k-local code Hamiltonians with polylogarithmic interaction degree. K is constant, and they have ground space approximate quantum error correcting codes that are good codes up to polylogarithmic corrections. So just a one-slide motivation about quantum codes. So abstractly, a quantum code is just a subspace of a larger Hilbert space that you use to redundantly encode quantum information so that you can recover it after an error channel acts on the states. But of course, in fault tolerance, we have additional considerations. I think it's fair to say that the majority of work on fault tolerance is focused on CSS stabilizer codes with local stabilizer generators. For example, the surface code. And these always give rise to local commuting Hamiltonians because, of course, the stabilizer generators all commute. But there's other reasons we might be interested in quantum error correcting codes in the ground space of a local Hamiltonian, because this is an indication that these short-range constraints are leading to long-range entanglement. And so this is of interest in Hamiltonian complexity, many-body physics, and maybe recently holography. So, and another motivation for our work is that we don't yet know the ultimate limits of quantum error correcting codes with local commuting checks. So what if we lift this restriction and ask what is possible to achieve with non-commuting code Hamiltonians? So to formalize this a bit more, there's something called the quantum LDPC conjecture, which asks, do there exist CSS stabilizer codes that have constant rate, linear distance, and local stabilizer generators? That's what it means to be a good code. Well, this table summarizes some of the work that making progress towards this question. So Tillich and Zamor gave a constant rate code with root n distance using local checks. If you just care about the distance, then Friedman, Meyer, and Luo gave this root n log n distance code with a constant number of encoded qubits. Hastings gave a code with a constant number of encoded qubits, almost linear distance, but the construction depends on a conjecture in higher dimensional geometry, so it's only conjectured to exist. Now, those were all CSS stabilizer codes, but there's also a work by Bacon, Flamia, Harrow, and Shi, which produces subsystem codes that have constant rate, approaching linear distance, and local gauge generators. But these gauge generators result in a frustrated code Hamiltonian. And also, another aspect of the analysis in this work is that it doesn't necessarily analyze the spectral gap of this non-commuting code Hamiltonian. So in our work, we produce codes that are good up to polylogarithmic factors. So this tilde above the omega hides a polylogarithmic correction, but basically it's almost almost constant rate, almost linear distance, local checks, but our codes are approximate codes, and they're in the ground space of a frustration-free, non-commuting local Hamiltonian. So what do we mean, what are our approximate codes? Well, we're going to relax the requirements of being a stabilizer code in two major ways. So we're going to have approximate error correction. So after an error channel acts on the state, you can only recover the encoded information up to some fidelity 1 minus epsilon. Also, our code space is the ground space of a frustration-free local Hamiltonian, but the projectors are not necessarily commuting. And so why am I making a big deal about frustration freeness? Well, it implies that you can do local tests for containment in the code space. So if you're familiar with gauge codes, because the gauge generator is anti-commute, they share no common eigenvalues. And so they can't be frustration-free. And so, you measure these gauge generators, you're just getting a bunch of plus or minus ones. You have to take large products of them together to ascertain the value of highly non-local stabilizers. But if your code is frustration-free, then these projectors have to stabilize the code space. And so if you see a violation in any of them, then you know that there's an error on the qubits where those terms act. Now, there's also a precedent in Hamiltonian complexity for these codes, and I would like to know more about the reason that they're defined this way in this paper on quantum locally testable codes. But yeah, so that's our framework. Okay, so now the main idea actually came out in a paper that immediately preceded ours. So the idea is to use the Feynman-Kitaev circuit to Hamiltonian construction to turn encoding circuits into history states which form approximate code words of the original code. So, the idea is, we've seen this a lot in this conference, you have this history state that is a superposition over time steps of a quantum circuit. Now, the idea is that, somewhere in this superposition at the final time step, you're actually describing the code word of the code that you're trying to approximate. Here's what the local terms, some of the local terms that check this Hamiltonian look like. So this superposition is kind of illustrated here. We have a superposition of time steps of the circuit. As you get to the end of the circuit, you're actually producing the code word that you wanted to. But in the beginning of the circuit, you get some noise. And that noise is the reason that our codes are approximate. So, what do you do in adiabatic computing? Well, you pad the history state in order to increase the overlap with the end of the code. With the end of the circuit, right? With the final state that the circuit produces. So you can do that, and then you can lower the approximation error of the code. So the first thing that we do in our paper is we kind of push this formalism to the limit by using something called modified circuit to Hamiltonian constructions, where we put in an arbitrary probability distribution over the time steps of the quantum circuit. So it turns out you can always construct parent Hamiltonians for these kinds of history states. And so here's what you do. You put 1 minus epsilon of the probability on the final time step, because that's the actual code word you're trying to produce, right? And you can control this epsilon. You can tune it to be whatever you want, okay? And so this leads to a result where you pick your own epsilon. It depends on n. It can be exponentially small if you want. Okay, then there exists an approximate error correcting code with these parameters, nearly linear rate, nearly constant rate, nearly linear distance, but the gap, you actually pay for this epsilon you chose. So as you tune down the approximation error of the code, you're actually tuning down the spectral gap of the code Hamiltonian. And the reason that happens is because of this input term here. Right? So this input term, there's some input checks in the circuit to Hamiltonian construction, which it only takes a small amount of epsilon energy to violate those. Okay? And this turns out within this framework to be the optimal trade-off between gap and error. This is a no-go from a paper I had with Johannes Bausch a few years ago. So what about bounded degree interactions? So if you think of classical LDPC codes, it's not only important that the code checks are local, but that there's only a constant number of code checks acting on any particular bit of the system, right? So this sparsity constraint also depends on having, uniformly bounded interaction degree. So the best we can do is to use good quantum error correcting codes with polylogarithmic depth encoding circuits. And these can bring the interaction degree of our code Hamiltonians down to order polylogarithmic in n. And the encoding circuits that we use were obtained by Brown and Fauzi in 2013. They show that random two-local Clifford circuits with polylogarithmic depth yield good quantum codes with high probability. This is based on the idea that random stabilizer states, random subspaces of stabilizer states are good quantum codes, and these low-depth quantum circuits kind of effectively sample a similar enough distribution. Okay, so but if we're trying to do something in sublinear depth, then it seems like we need to parallelize our circuit to Hamiltonian construction. So that brings us to the SpaceTime Circuit to Hamiltonian construction, where you don't just assign one global clock and do one gate at a time, represented by this particle hopping on a line, but you actually assign a separate clock to each qubit, and you allow those to update independently. So the propagation terms of the Feynman-Kitaev Hamiltonian only update clocks on which the gate acts. So here it's illustrated for a 1 plus 1 dimensional quantum circuit. So here's space, here's time, and this red line represents a possible time configuration of these clocks as they proceed through the circuit, right? And as you do this, it's important to enforce what are called causal constraints. So we're only interested in these time configurations that could have arose from a valid operation of the circuit. So a time configuration is valid if when there's a gate acting at time t on qubits q and p, you'll always find either both clocks less than time t or both clocks after time t. Never one of them after and the other before. Now, because the causal constraints depend very much on the geometry of the circuit, they also affect the diffusion of this string membrane and have an important effect on the spectral gap. Actually, just a reminder, so when you analyze the circuit to Hamiltonian, you're analyzing this single body hopping particle to get the spectral gap. But when you analyze the space-time circuit construction, you actually have to analyze the diffusion of this string through this circuit. So you're effectively going from a single body problem to a many body problem. Okay, so now what has been done before with these space-time Hamiltonians? They're hard to analyze. So previous analyses have relied on a mapping to exactly solvable 1 plus 1 dimensional quantum spin chains. You know, it's very beautiful. I wrote the Heisenberg equation here. It's actually a little more complicated than that with the boundary conditions, but you know, effectively we know there's these 1 plus 1D exactly solvable models. There's this connection between quantum models and stochastic classical kinetic models that describes the diffusion of this string through this circuit. Okay, and they get a gap scaling and it's great, but you know, if you tried to take an arbitrary low depth circuit and map it to 1 plus 1 dimensions, as many of us are doing in the context of NISQ architectures, well then, you know, you're gonna have to use a bunch of swap gates and you're gonna blow up the depth quite a bit. So we need something more depth efficient, and to obtain that, so okay, first I should mention that the Brown-Fauzi circuits, it's a randomized construction. So we could try to actually analyze that random geometry. That turned out to be hard, so instead we uniformized the circuit connectivity by using something called Bitonic sorting networks between every layer of quantum gates. So this is just a particular sorting network. So you imagine these wires come in, and here you have gates that are conditional swaps if you need to get the right permutation out. So these Bitonic networks only blow up the depth by this polylogarithmic factor and let you do arbitrary permutations between the gates. And in fact, as a bonus, they're spatially local in log base 2 of n dimensions. So the gates are effectively acting along edges of the hypercube in this many spatial dimensions. And actually what we do, if you look at this gray box, this is important, we call it a Bitonic block. And we actually just we add some extra padding to in here and here. So it just looks like Bitonic blocks over and over. So our actual construction looks a bit like this. We put it on a circle for various reasons. So you do some Bitonic sorting circuits, you apply a layer of quantum gates, Bitonic sorting circuits, and so on. You actually, and then you undo the gates to come back around, but you actually always keep the Bitonic sorting circuits moving the same way, again, for technical reasons. Okay, so let's look at what we have to analyze. So here's a string sitting in the middle of this long array of Bitonic sorting circuits. Okay, here it's going through some moves, right? So this is a Markov chain where we're doing little local moves on this string in this highly constrained, high-dimensional configuration, right? So how are we going to have any hope of analyzing this, right? This complicated process? Well, we're going to use a relatively high-powered tool called the Markov Chain decomposition method, okay? So consider a Markov chain with stationary distribution pi, transition probabilities p, and state space omega. So what you do is you break up omega into a bunch of overlapping subsets that union together to give you the original set. All right, so define this B to be the maximum number of subsets that contain any one configuration. And now define what's called the aggregate chain that moves between these blocks. So this block omega 1 can jump to this block omega 2 under this aggregate chain P bar. And the probability of doing that depends on the stationary probability in the intersection of the two blocks. So So that's the aggregate chain. Now we also have to define a restricted chain in each one of the blocks. So this is just the restriction of P to one of these subsets, and you do that by just rejecting moves that would ever leave their respective blocks, okay? And the theorem that's used in the Markov chain literature, so the gap of our original chain is lower bounded by the product of the gap of the aggregate chain and the minimum gap of any of the restricted chains. Okay, so how are we going to apply the decomposition method to our problem? So we choose a decomposition where each subset of our state space contains all configurations that lie within one of these colored rectangles. So all valid time configurations propagating in this red rectangle, that would be the block omega 1, right? And all valid time configurations in the green block, that would be omega 2. So to start by analyzing the aggregate chain, we need to count the number of configurations in this intersection. Okay, so let's focus on the first red block and the first green block. So let's think about the time configurations that are here in this region where they intersect. Okay, so now if AL is the number of configurations in the red block when it has 2 to the L wires, then actually you can see that the size of the intersection is AL minus 1 quantity squared. Why is that? Well, if you're constrained to lie in this intersection, then you can't touch these gates. And look, you have kind of a recursive copy of a Bitonic block on a smaller subset of wires. Okay, so you start to build a recursion relation. And if you do this, you can build up a recursion relation that counts the number of configurations in one of these blocks. And actually, this recursion relation has an asymptotic solution in terms of the golden ratio and also this constant omega that doesn't have a closed form. So when you do this, you can actually compute the aggregate transition probabilities exactly. And then, so if you look at the connectivity of this blockchain, right? So so, you know, red, green, blue, right? Red intersects blue, red intersects green. That's what these edges are, right? It's effectively like a linear chain. If you just coarse grain a little bit, it's like a linear chain. So you can just, you know, apply Cheeger's inequality and get kind of the expected bound. If there are m sites in a linear chain, you know, your gap is like 1 over m squared. Okay, but it turns out that the online encyclopedia of integer sequences also knows about our recursion relation from a completely different context because it counts dyadic tilings of the unit square. So what is a dyadic tiling? Well, it's a tiling of the unit square in terms of equal area dyadic rectangles that, you know, are defined in terms of coordinates of powers of 2, but the way to think of them is like this. Okay, you have a square, you put down a vertical bisector, and it breaks it into 2 rectangles. You can put down either a vertical or horizontal bisector in each one of them, and you do this recursively, right? So at each level of the recursion, you choose either a horizontal line or a vertical line, okay? So that's how dyadic tilings are defined. That's the counting correspondence. But there are also a natural dynamics on these dyadic tilings, which is called the edge flip Markov chain. So the way this works is that you randomly select, so in your Markov chain, you randomly select one of these rectangles, and then you randomly select an edge within that rectangle, and you propose to flip it if doing so would yield a valid dyadic tiling. Okay? Now, the mixing time of this edge flip Markov chain was an open problem for almost 20 years. Okay, but it was recently shown to be polynomial in 1 over the area of the squares. Okay, all right, so maybe you can guess what's going to happen. All right, so we actually have a correspondence between the edge flip chain and our restricted within block chain. So, and the correspondence is color coded here. So the red gates here correspond to the red edges. All right, and when we move through one of these gates, we're going to flip a corresponding edge. So, let's start by moving through this gate here. Okay, we move through it and we flip that top red edge. Okay, now let's look at what we can do. Well, we can't flip this green because that wouldn't yield a valid dyadic tiling. We can't flip these blues. We're going to have to do another red. Okay, there we went through another red gate. See how it corresponds to the fact that we couldn't have gone through any of these green gates yet. We can't go through any of these blue gates yet. But now that we've done 2 reds, we can actually go through one of these greens. See, we're ready to go through this green here. Okay, there, we went through it. Oh, yeah. Oh, I should have said that when the edge is horizontal, it means we haven't gone through the gate, and when it's vertical, it means we have. Okay, so you can proceed in this manner as you go through the circuit. Okay. So are we ready to do any blue gates yet? No, because they wouldn't yield a valid dyadic tiling. Well, what's happening here? Well, this guy's ready to go through a blue gate, but its partner's not. Its partner's all the way back here. Okay, so maybe we should flip that red right now. Okay, so we do that. So now are we ready to flip that blue? No, not yet. Okay, but what are we ready to do? Maybe another green? Nope. Oh, sorry. Yeah, we're ready to do a green. And now we're finally ready to do this blue gate. And that corresponds to this edge that we're going to flip here. Okay? So now you can move through this, and the correspondence is just perfect. Okay. All right. So putting this all together, what we find is that for any depth D quantum circuit, you can insert these polylogarithmic depth Bitonic sorting circuits and analyze the gap of the resulting space-time circuit to Hamiltonian construction. And this gap turns out to be polynomial in your number of qubits, number of qubit wires, and the depth. Okay. And you could apply this, for example, to adiabatic computing or QMA completeness constructions. This is perhaps a result of independent interest, right? How rare is it that we can actually analyze the spectral gap of any spin model in a high number of spatial dimensions? All right. So I apologize if I went a little fast. But actually, there's a ton more to say about our results. But actually, here's a bit of bad news. After we went through all that and found this awesome correspondence, we turned out that we could make some modifications to the original FK construction and actually end up using the global clock. And the analysis is much simpler. Okay, so, is there any point to the space-time construction besides just looking pretty? Well, it turns out that actually, yes. So what we did is there's a section in our paper where we analyze the energy of states that are created by acting with arbitrary Pauli errors. So we just do this by brute force, right? You know the ground state, this history state, you act on it with, X acting on a clock qubit and Z acting on a computational qubit. We do all kind of patterns like this to cover all the cases, and we show that in every case for the space-time construction, the energy after you act with a Pauli error is bounded by 1 over the depth, bounded in terms of 1 over the depth, whereas for the global clock construction, it goes like 1 over the size of the computation. So if you're actually going from a polynomial size circuit, if you're going from a polylogarithmic depth circuit, but with polynomial size, this is like an exponential improvement in the exponential increase in the error of acting, in the energy of acting with one of these tensor product of Pauli operators. And so basically then we actually write out, you use kind of QMA style amplification, you can locally test for containment in the code space. And this energy after you act with the errors is related to the depth of these amplification circuits. So, what we're doing here is we're not saying that, you want to go out and build a fault-tolerant computer necessarily using these codes, but we're trying to take some steps to examine that direction, right? Let's not just say that they're abstractly codes in the ground space, but let's actually see what happens when some errors come in and act on the system. So there's actually a full section in our paper about that. And so now the main open question is that this framework can't achieve constant degree, because doing so would be like having a constant depth encoding circuit, or some kind of improved history state construction because of the way that our interaction degree is related to the number of gates acting on any particular qubit. So in my mind, it's still pretty interesting if you can get something that's a good approximate LDPC code according to our definitions in the ground space of a k-local Hamiltonian with constant interaction degree. That would require major new ideas. Thank you.
Okay, so we have plenty of time for questions. Daniel.
So can you say a bit more about this as a quantum error correcting code? Do you know how you'd actually use it to correct errors, decoding procedure?
Yeah, that's a good question. So we actually use adiabatic computation to do the encoding. But as far as the decoding, so remember the frustration-free local checks, because they stabilize the code space, you can kind of measure big patches of them at once with a reasonable depth amplification circuit. And the reason for using amplification is you want to get the right answer if there's an error there or not, right? Because these checks don't commute. You would have to break them into multiple layers. So the point is, if there's an error, you kind of want to amplify your detection of it so that you definitely detect it. And then if you do detect it, well, I guess what you would do is you would throw that part of the system away. Okay. Well, again, we don't have a complete fault-tolerant scheme, so I'm about to say something that's not fault-tolerant, right? But then you could adiabatically drag back, and your state is completely unprotected, and then you could refill in that part of the code word and then adiabatically go back again.
Other questions?
You used Bitonic sorting network, but is it possible to replace this sorting network with other sorting network, or is your analysis depend on this?
Yeah, absolutely. So, this part with the dyadic tilings is kind of special to the Bitonic sorting circuits, but actually this idea of having kind of this box that slides along, I think is a good way to analyze SpaceTime Circuit Hamiltonians with various connectivities. But one thing I will say about that is that, one thing that's kind of crucial is that our configurations, our time configurations never get too far, they're not too wide. We call it the width of the configuration. So like, what is the difference between the earliest clock and the latest clock is never more than logarithmic. So for example, like I should say, an open problem is, so this thing with the 1 plus 1D circuits, if you could do this in 2 plus 1 dimensions, you would, solve open problems in mathematical physics about like surface growth, right? But you wouldn't want to use this strategy there because basically you can have these long light cones and the blocks would get too big. But yeah, there are ideas in here that could be repurposed, yeah.
Other questions? I have a question.
Yes.
So you said that you analyzed the energy for arbitrary Pauli errors. Did you mean single qubit or arbitrary tensor product of
products of
Paulis?
Paulis.
So do you know something about the energy barrier? That's
So-
just the energy of the putting down the error all at once.
That's the energy of putting down the error all at once as a big non-local error. And when I say that it's 1 over, poly log of n, that's only in the worst case. A lot of times it's constant, and it could be even more. So we're just kind of, worst case, I mean the lowest energy that the big
Right.
error could have. But in some sense, those errors are almost adversarial. Like if you put down, there are many errors that actually could give you a large energy, definitely.
But you don't know anything about the energy barrier then?
No.
Like to get to one of those, I mean, it's low energy. It's not that low, right?
Sure.
But to get to it, you might have to cross some large mountain.
Sure. And it would be interesting to talk about how to even properly define that for this non-commuting case.
Oh, right.
Yeah.
Other questions? Yeah, we have some time.
So my original question was about whether or not this was special to the Bitonic sorting network, but you already answered that. So, but then you said that you think that this strategy using shifting window should be generic for circuits where the sort of string representing the clocks does not, become too pointy or something, or it doesn't stretch too far along the. So, is there? Do you think you can? Is there a chance to sort of make that precise? It seems like that would capture a pretty wide family of quantum circuits. And so.
That would be great, and it's definitely worth exploring. And if you think of the way that the decomposition is kind of set up, it's designed in such a way that the aggregate chain is the easy one, and the within block chain is the more difficult one. So that was the one where we, needed this miraculous correspondence, whereas, the aggregate chain I mean, anytime you could count these configurations in the intersection, you could analyze the aggregate chain, right? Effectively, because it's quasi-linear connectivity, you just have to show the transition probabilities aren't super small.
We still have some time for questions.
Okay, so one question is, what disturbs you from making this go to 2 plus 1?
Oh, yeah. Well, you know, many things don't work, right? This is like spatially local in log n dimensions, right? So you couldn't fit these Bitonic sorting circuits in 2 plus 1. And basically, the thing that I was saying earlier is that when you're in any fixed number of spatial dimensions, the light cones are just too long. So the blocks have to get too big, right? Like if you think about a 1 plus 1, I mean, it's too much, right? Like this could be, your clocks could be n apart. And so you effectively haven't even reduced the problem to a smaller one. Yeah.
We still have time for questions.
Sorry, everyone.
Hi. I have a question. So you're starting from the encoding circuit of some stabilizer code,
Yeah.
and then you get this Hamiltonian. So is there, do you know a relation between the terms in the Hamiltonian you get at the end, and then I don't know some properties of the code, like the stabilizer of the original code or something?
Okay, yeah, that's really interesting. So you could imagine taking products of the local check terms in the Feynman-Kitaev Hamiltonians, right, and trying to ascertain the value of non-local stabilizers. So actually this has some relation to subsystem codes because there's this clock register that is effectively like a gauge subsystem. You don't care when errors act on it, right? So we wanted to kind of complete that and say that if you could measure all of these local terms, then you could product them together to get the stabilizers of the original code. And the reason you can't do it is because you have to measure them in different commuting layers. So you can't, the things that you have to product together, you can't measure them all simultaneously, unfortunately, unlike something like the Bacon short code.
Any other questions?
I might have missed it, but why do you have the distance that scales, as you say?
Why do we have that distance? Yeah. So so let's see. So what we're using are short depth encoding circuits that yield good quantum error correcting codes. So you keep most of the distance and rate of the original code. It's just that you've added these clock ancilla and they slightly reduce your distance and rate. So effectively, you retain, up to polylogarithmic corrections, you retain the properties of the original code that had highly non-local stabilizers.
Any more questions? We have time for one more. Good thing you had a really interesting talk. This would have
Every
been
time
10 minutes of silence. I'd
Every
have to
time I
sing One
practiced
Entangled
it,
Evening.
It went too long.
I was intrigued by the 17 in the. Is that have something to do with 2 dimensions and
Yeah.
wallpaper
I mean,
groups or?
Yeah. So that of course came from that paper by those Markov chain experts. So this was the log base 2 of 17. Yeah, this factor here, which is in this paper, and you know they actually use something that's a lot like a block decomposition analysis too. So you know their analysis of how this Markov chain converges, basically instead of doing these little edge flip moves, you take larger and larger regions of the dyadic tiling and do like a big move at once. So they're actually using some similar techniques. You know, maybe we could have analyzed it from scratch if we had done it that way. Yeah.
Okay, let's thank Elizabeth for a wonderful talk.